Hi, my name is Eli Bell. Today I'm going to be going over problem 37 from 1310, exercises for Lagrange multipliers. This is for my discussion 10 post. I'm going to be doing this problem in a couple of different ways just because I was curious to see how the different approaches compared and the pros and cons of each. So, we need to maximize f of xy equals sine x sine y, where x and y denote the acute angles of a right triangle. So first thing, let's think about our constraint. We have a triangle, so we know that the angles add up to 180 degrees. And our triangle is a right triangle. So we have 90 degrees plus x plus y equals 180 degrees. So x plus y equals 90 degrees. And then we're going to be using lots of trigonometric functions. So we want that in radians. So what is 90 degrees in radians? That's pi over 2. And then solving for y, pi over 2 minus x. Now, the first way that I'm going to be doing this problem is more of a Calc 1 approach. So we're just going to take this constraint and we're going to plug it right into the original function. And I'm going to define it as a new function in terms of just x to eliminate the y component. So f of x equals sine x sine pi over 2 minus x. Now we can simplify this. So sine of pi over 2 minus x, that's a phase shift. So that actually just equals cosine x. So we have sine x cosine x. And this is actually equivalent to another trigonometric identity. Sine x cosine x equals 1/2 sine 2x. So now we can derive f. So f prime x equals 1/2, and then the 2 comes out, so 2 cosine 2x. Of course, these 2's cancel out, so we just get cosine 2 of x. So now we have to set that equal to 0. Set cosine 2x equals 0. All right, so when does cosine equal 0 that's within our domain? That would be at pi over 2. So we have 2x equals pi over 2. And then solving, we get x equals pi over 4. All right, so now we can take that x and we can plug it back into this equation to get y. So we have y equals pi over 2 minus pi over 4, which just equals pi over 4 as well. So now let's check if it's maximum or minimum. We know it's an extrema, but we have to check. And this is equivalent to our second partials test, but just the Calc 1 version. All right, so let's derive f prime. So we got f double prime of x equals, let me scroll up so we can actually see, All right, so that's just going to be negative 2 sine 2x. All right, so now we can just take our x value and plug it in to f double prime. So that's pi over 4 equals negative 2 sine 2 times pi over 4. Simplifying this, we get pi over 2. We know that sine pi over 2 is 1, so this just equals negative 2, which of course is negative, less than 0. Therefore, this is concave down, which means it is a local max, which is what we want. All right, so now let's plug our critical point back into our original equation. So we have f of pi over 4 equals, and then it's sine. So sine pi over 4 times sine pi over 4. And what is sine pi over 4? That is root 2 over 2. So root 2 over 2, and then the second term is the same thing, so we can just square that, equals 2 over 4, which equals 1/2. All right, so we have our maximum value, and we're ready to write our conclusion. So, f has a max of 1/2 at pi over 4 pi over 4, subject to the given constraint. And we can also note that pi over 4 is equal angles. So the triangle that we get that maximizes this function is an isosceles triangle. All right, so that's it for the first approach. Okay, so now we're going to try to use the second partials method to solve this problem. So f of x, y equals sine x sine y. And we should note that x has to be greater than 0 but less than pi over 2. And same for y. And this is because they are angles, or they are acute angles of a right triangle. So step 1, let's just get all of our partials out of the way. So fx of x, y equals cosine x sine y. Fy xy equals sine x cosine y. All right, and then we got f double x here. And the cosine is going to go to negative sine x sine y. Now f double y. Oops, forgot my equal sign. All right. Sine x sine y. Some nice symmetry there. And then let's get our mixed partial. That's going to be cosine x cosine y. Now that we have our partials, we can take fx and fy and then set them equal to 0. So, step 2. Fx xy equals cosine x sine y equals 0. And then we have fy xy equals sine x cosine y equals 0. And I should say set fx and fy equal to 0. All right, so just looking at the first quadrant, what would make this true for cosine x? That would equal 0 at x equals pi over 2. Oops. 2, and then y would just equal 0. And looking at the other one, it would be the same thing, but flipped. So y equals pi over 2, and x equals 0. All right, so that gives us our critical points of 0, 0, and pi over 2, pi over 2. So 0, 0, obviously we have to reject that because we can't have angles of 0. So reject. And then pi over 2, well, if we scroll up here and look at our domain, that's actually not in it either, since it's open on pi over 2. So I guess we have to reject that one as well. So reject. And that makes sense because if we had an angle of pi over 2, that would be 90 degrees. So we know we have a right triangle, so that would definitely be over 180 degrees if we had 3 right angles. That is simply not possible for a triangle. So what to do now? Because it feels like we've hit a dead end. So I was thinking maybe the extreme value theorem, where we find the absolute extrema on a closed bounded region. But then I realized that our constraint is not closed. It's open here since it does not include the boundary. So I think that we just found all of those partials for no reason. And the second partials approach is just not really applicable to a constraint problem like this, especially where you don't have a closed bounded region. I think if you wanted to move forward from this point, it would just kind of become what we already did in the Calc 1 approach. So I was wondering before, like, when to use second partials, when to use Lagrange multipliers. So it looks like this is a situation where using the second partials approach just doesn't really work, or doesn't allow us to arrive at the solution. So now let's look at the Lagrange method. Okay, so now let's actually use the Lagrange method. So we need to maximize the function f of xy equals sine x sine y. So maximize f of xy equals sine x sine y. Subject to the constraint, so constraint, which we'll call g of x, g of xy equals x plus y minus pi over 2 equals 0. So now let's get our gradients. Fx xy equals cosine x sine y, and then fy equals sine x cosine y. Alright, so our gradient is, for gradient of f, equals cosine x sine y, comma, sine x cosine y. Alright, and then the gradient of our constraint, g, well, that's easy. It's just going to be 1, 1. So g Alright, so now we can apply this to our Lagrange equation. So gradient of f equals lambda gradient of g of xy. Alright, so we have cosine x sine y, comma, sine x cosine y equals lambda 1, 1. And then we can distribute that lambda, and we end up with our two equations in terms of lambda is lambda equals cosine x sine y, and lambda equals sine x cosine y. And without even rearranging, we can just eliminate lambda and set those equal to each other. So cosine x sine y equals sine x cosine y. So let's bring this all to one side. Cosine x sine y minus sine x cosine y equals 0. And this is actually an identity. We can use here the sign subtraction identity, which says sine A minus B equals sine A cosine B minus cosine A sine B. So we can just reduce what we had up here to sine x minus y equals 0. Now let's solve for x and y. So what would make this true? We know that, let's see, sine theta equals 0 when x minus y equals some multiple of pi. So that's, where k is an integer. All right, and let's note our domain because that's going to be relevant here. So x is greater than 0 and less than pi over 2. And, all right, same thing for y. All right, so let's start with k equals 1. Okay. So if k equals 1, then x minus y is going to equal pi. All right, so is that possible with our domain? Let's see, the maximum that x could be is pi over 2, well, not quite pi over 2, approaching pi over 2. And the minimum y could be would be just on the right of 0. So no, we could never get pi, so we're going to have to reject this. Reject. All right, and we're not even going to try 2 or anything higher because that would just make this even further away from what we want. So let's try -1. So x minus y equals negative pi, and I think we can already see same thing. There's no way we can possibly get that given our domain, so we're going to reject that as well. So the only thing left to try is k equals 0. So x minus y equals 0. Which means that x equals y. Great, so recall our constraint function, x plus y equals pi over 2. Now we can just substitute in x for y, so x plus x equals pi over 2. So that's 2x equals pi over 2, which means that x equals pi over 4. And since x equals y, we also know that y equals pi over 4. All right, I just minimized this stuff to give us some more room. So now we have the point pi over 4 comma pi over 4, and that is our Lagrange point. Lagrange points. So we need to test if that's actually a maximum, because it could also be a minimum or saddle point. So let's pick convenient values on either side of it. We're not going to use the endpoints just because they're not defined here. So I think the convenient values to use on either side would be pi over 3, comma, pi over 6, and pi over 6, comma, pi over 3. These are our test points. Okay, so now we can just plug these into f. So f 4, comma, pi over 4 equals sine pi over 4 times sine pi over 4, so we can just say squared equals, and then what is sine pi over 4? That is root 2 over 2, so root 2 over 2 times itself, and we already know from doing the previous approaches that this is 1/2. So now let's do the same thing for our test points. So we have pi over 3, comma, pi over 6 equals sine pi over 3 sine pi over 6. And what is sine pi over 3? That is root 3 over 2 times, and then sine of pi over 6 is 1/2. So we end up with this, which is approximately 0.4 something. So we know that that is less than 1/2. And then let's check the point on the other side. So this one is pi over 6, comma, pi over 3. Sine over 6, sine pi over 3. And we already know that that's going to equal the same exact thing. So root 3 over 4, which is 0.433 something, so that is less than 2. So therefore, we have a relative max because this value is greater than the ones on either side of it. So therefore, f has a relative max of 1/2 at pi 4, comma, pi 4 subject to the given constraint. To the given constraint. All right, so that is the Lagrange method on this problem, and it matches our answer from the first approach, but not the second approach because that wasn't really applicable for what we were trying to do, so we ended up at a dead end. But the Lagrange method was pretty straightforward here, and we got what we wanted. I just wanted to share a graph of everything. So in the middle, you can see our surface curve, and then that plane over there is the constraint that x plus y equals pi over 2. I feel like there's a way to maybe change the axes units in terms of pi, but I couldn't figure it out. But that would have been nice. Anyways, I put a point on the solution, the maximum, and you can see it there. I have the trace over the constraint highlighted, and then you can see the contour curve, that's the red line, at z equals 1/2. So anyways, that is it. Thank you.